This is part 5 of the series Reasoning and Proof, and in the last part we had begun talking about properties of equality. We left off with the division property of equality, and we're going to move on to the next one, which is the substitution property of equality. What the substitution property of equality says, if x equals b and a times x equals c, then anywhere there's an x, we can replace that x with the b. We can substitute b in for the x. So this ax equals c becomes ab equals c. Now you've done this several times. If you were looking for a specific value of something and you were given that a value of x was some number. Let's give an example here so that we don't get confused. So let's say that I told you that x equals 2, and you had the expression 2x plus 3 equals, let's say it equals the height of something. So we would substitute the 2 in for the x. So we'd say 2 times 2 plus 3, which would give us 4 plus 3, which would be 7 equals. This would be a use of the substitution property of equality. To substitute some value in for another variable or another value, and that does not change the equality of your statement. The next property that we're going to talk about isn't a property of equality, it's simply a property, and it's called the distributive property. Now you've probably used this many times in this particular way to say that if a times the quantity x plus y, then you can say that a times x, we distribute the a throughout each one of these terms, a times x plus a times y. But a lot of you may not know that the distributive property also works in reverse. If you have this situation, you have a common a term in factor in both of these terms, we can factor out this a. We can divide it out using the distributive property. If we pull out this a and say this equals a times the quantity of ax divided by x plus ay divided by a, we would get a times x plus y. So the distributive property doesn't just work this way, it works in reverse as well. So that's the distributive property. And you're going to use that in both respects, both going this way and going in the reverse order. Let's move on to another set that you probably haven't seen before. This first property is called the reflexive property of equality. Now, every time I bring this up, I run the risk of people misremembering the name of the property. And if you look at this, what it's saying is that the value is the same on both sides of the equal sign. That's the reflexive property of equality. And the way you can think of it is you can think of it as looking at your reflection in a mirror. Unfortunately, there's a tendency for people to remember reflection instead of reflexive. The property is the reflexive property of equality. So when the value is the same on both sides of the equal sign. Now this works for real numbers. If you have real numbers a and b, or a, b, and c, or whatever, a equals a, b equals b, c equals c. Line segment lengths, segment AB equals segment AB, angle measures. The measure of angle A equals the measure of angle A. Now it may seem kind of silly to do something like this, but you're going to see later on where it's actually necessary when we have to work with triangles and prove two triangles are the same, or if we're trying to prove two lengths of segments are the same, we will be using this reflexive property quite extensively. So it seems kind of trivial, but it is very relevant. Let's move on to the next one. Now this is called the symmetric property of equality. And what it says that if A equals B, then B equals A. So we can basically swap things from both sides, across both sides of the equal sign. And this is what allows us to do things like, now I don't know about you, but when I'm working with algebraic statements, I like to have something like this, x equals 2. But sometimes you may be working a problem and you might get 2 equals x. Well, this symmetric property of equality allows us to go from here to here. And it's perfectly valid because we can swap things on both sides of the equal sign and it doesn't change the equation. It keeps it exactly the same. So that's the use of the symmetric property of equality. And it's really more for form than anything else, but it's still a valid property to use. This works for, again, real numbers, segment lengths, angle measures, anything that can be set equal to each other, just like this. Let's move on to the next one. Now, this next one is a little bit more complex. Now, this property is called the transitive property of equality. And it says if A equals B and B equals C, then A equals C. Now, if you think, this should look very familiar to you. Can you think of where we just saw something that looks like this? If you said the law of syllogism, you'd have been correct, because this is the property of equality that is analogous to the law of syllogism in our logical laws. There are some distinct differences that we're going to look at a little bit later on, but this is the basis. The law of syllogism is the basis for the transitive property. And one of the fundamental differences is it doesn't matter which side of the equal sign these guys fall on. I could rewrite this to say if A equals B and C equals B, then A equals C. And the reason we can do this in the transitive property is because of the symmetric property. I can take this statement and I can swap it using the symmetric property to change it to B equals C. And therefore we have A to B, B to C, therefore A to C. So in the law of syllogism, where it disallowed this condition where the values could be on the same side, in the law of syllogism, remember, they had to cross. Well, here they don't have to, because we have additional laws and properties that allow us to swap sides. And you can't do that with the law of syllogism. So that's one of the distinct differences here. So the important thing is to see the pattern, that you have something repeating. And if you have that something repeating, then this goes to this goes to this, therefore this goes to this. That is the essence of the transitive property of equality. And it works for segment lengths. AB equals BC, BC equals CD, therefore AB equals CD. And it works for angle measures. A to B, B to C, A to C. Now, as I stated at the very beginning of this series, this is the thing that distinguishes geometry from all other forms of mathematics that you've probably studied up to this point. And that is that we have to justify every step we make. And that's what we're going to be doing with these properties. We're going to be taking these properties and definitions that we've learned about so far and all these rules, and we're going to use them to justify our statements as we solve different problems. So let's go ahead and see an example of what we're talking about, and we'll use a basic algebraic example to exemplify what we're talking about. So in this first example, in justifying steps, we have this basic algebraic equation. And I want to solve the equation, but I have to give a justification, a valid mathematical reason for doing every one of the steps that we're going to do. All right, well, the first thing I'm going to do is I'm going to go ahead and write down what we have here. So let's start off, let's do it over here. And let's say we have 4x plus 3 equals, that's supposed to be a 3, 21 minus 5x. And the justification for that statement is, we're going to say, given. That's the information that was given to us. So we're going to use that as our starting point. Now, where you go from here is your choice. And it's purely stylistic. You can do anything you want. You can combine your constants. You can combine them on the left, combine them on the right. You can combine your variable terms first. It doesn't really matter. The only issue is that you give a valid mathematical reason for every step that we do. And we're going to use the properties, definitions, and rules that we've talked about so far to justify these steps. Well, because I don't have you talking to me, I'm going to just do what I normally do. I'm going to combine my x terms, and I'm going to combine them on the side that gives me a positive x value. So I'm going to combine my x terms on the left-hand side. That means I'm going to add 5x to both sides. So I'm going to add 5x, and I have 9x plus 3 equals 21. Now what I did was I added 5x to both sides. Do you remember what that property was? That is the addition property of equality. So that's a valid mathematical justification for how we got from this step to this step. Now I'm going to go to my next step, and here I'm going to move this 3 to the other side. Since that's a positive 3, I'm going to subtract 3 from both sides. So that gives me 9x equals 18. And that is the subtraction property of equality. And now I have to get rid of this 9 from the x term here. So since 9 is being multiplied by x, I undo that multiplication by a division. So I'm dividing both sides by 9. And that is the division property of equality. Let's go ahead and work another problem and see if we can use a couple of new properties. Here we have 3 times 4x plus 3 equals 45. And again, we're going to say that's our given. So that's our reason for this. Now we have two choices here. We can either distribute the 3 inside these, or we can divide both sides by 3. It really doesn't matter one way or another. I would probably opt to divide both sides by 3, but then we wouldn't get to use the distributive property. So let's go ahead and distribute the 3 to each one of these two terms. We have 3 times 4x, which is 12x. 3 times 3 is 9, equals 45. And you may think, oh, we multiplied, so that's multiplication property. No, we didn't cross the equal sign. It's all on one side. So when you're doing the multiplication on one side, it's just the distributive property. We've distributed the 3 to each one of the terms inside the parentheses. So that's distributive property. I like to abbreviate. So let's now go ahead and we'll subtract our 9. So we would say 12x equals 36. And since we subtracted 9 from both sides, that's the subtraction property of equality. And then we're going to divide by 12. So x equals 3. And that's division property of equality. It's not terribly difficult. The key is to figure out what step allows me, what justification allows me to go from here to here. This justification allows me to go from here to here. This justification allows me to go from here to here, and this from here to here. And that's all there is to it. Now this leads us to a more formalized description of this justification of terms, and that's called a two-column proof. And we're going to look at that starting in the next video. And so let's move on to that, and I will talk to you in the next video.